Week 6 and lecture 3. Previously, we were talking about pointers. You'll remember that. And pointers were about the addressing modes. We have the addressing modes in these slides somewhere. Yes, right here, the addressing modes. So it was about indexed addressing. So if you want to reach somewhere in the memory, we used index addressing, which is these square brackets, and the square bracket meant that this is an address in the data memory. Very clearly, I mean, R2 has a value. If R2 is this value, for example, it was pointing to that value in the memory. And at that memory location, there was a number. And if the instruction was, for example, 32 bits, since 32 bits were made of 4 different 8 bits, 4 times 8 equals to 32. Since LDR is by definition at 32-bit, in other words, 4-byte operation, I have read the number starting from this address, counting 4 cells in a little endian manner. What was the little endian manner? Lowest address will be the least significant byte. So at the lowest address, I have this byte. Next, the next byte. And at the highest address, starting from these addresses, counting 4 address values, I had the most significant byte. So this was all about, actually, this operation, this index addressing operation of more than 1 bytes, makes a summary of a lot of things. Instructions being 1 byte, 2 byte, or 4 bytes. In other words, 8-bit operations, 16-bit operations, or 32-bit operations. They are by definition like that. LDR is 32-bit. You'll remember LDR-H. H stands for half there. It stood for 16-bit operations. So the organization of the memory, little endianness, how we read the data, how we get to that part of the memory, we use pointers, where we keep the pointers, where pointers are addresses in the data memory, all of them, all this information, all this knowledge are inside this addressing mode, which is called the index addressing mode. So by knowing this, we can always access a part of the memory, read some values in and out. By STR, we could write to the memory as well, or read from the memory using LDR, and we'll have our data. Cool, cool.
Hocam bir şey sorabilir miyim?
Please.
Bunun kullanım alanı C#'daki pointer'la aynı mı?
Not exactly technically the same, but the word pointer is the same. So in C# you have pointers, in Python you have pointers, in even MATLAB you have pointers, in Java you have pointers, and here you have pointers. Pointers means that variable is pointing to a place in the data memory. So the value of that, if a variable is pointer, that value is actually an address location in the data memory. So yes, they are the same, and it all means the same. A value, an address value in the data memory. Okay?
Okay.
Okay, thank you. So we talked about endianness, and we were defining the pointers. We are going to use pointers. So whenever I write a code and read a code, I'd say that I'm giving this value a pointer. I'm making R2 a pointer. How do I know that it's a pointer? Because I'm going to be using R2 inside the square bracket. That's why it's a pointer. I understood that it is a pointer by reading the code, further lines in the code, and judging by the fact that it's inside the square bracket, okay? Okay, so it is us who knows that R2's value is a pointer. I mean, you could use a value like this. Maybe you're trying to sum up this value with another value. How do I know that this value is a pointer? In only line 56, I don't know. But looking at line 57, using R2 inside the square bracket, then this must be a value. This must be a pointer, I'm sorry. This value must be a pointer. And that pointer this is a value in the unless memory. Actually, we are going to do this today. We are going to be looking at the memory, pointing that memory. We did it last time. We are going to do it again. Now, please.
Önceki slide'ı bir açabilir misiniz?
Please. So this one, I guess you're talking about this one, right?
LDR-H, neden LDR-H'i yazdığımızı soracaktım da.
Yeah. What we also said was, I understood the question. Your friend is asking, what is the difference between LDR and LDR-H? Okay, when we are trying to understand what this instruction does, we are doing many things. The first thing we do is we look at the value of R2. I think you get that. Inside the value of R2, I have this value because R2 is a cell, a hotel room. Inside it, there's a 32-bit value. And since it's in a square bracket, I'm getting that it's a pointer. So this value must be an address in the data memory. I'm looking for the hotel room in the data memory with this number on the door. It is here, okay? This is LDR, load register. It's going to read from the memory right to the registers. It's going to read a value from the memory starting with this address and write it to R1. But starting with this address, at this address, I have an 8-bit value because in my memory, each cell only can keep 8-bit information. Am I going to only read 8 bytes, which is 8 bits, or 2 bytes, 4 bytes? Who decides that? The type of the instruction decides that. LDR, by definition, is a 4-byte operation. That's why I'm reading 4 bytes. If I had LDR-H, which is another instruction with a similar purpose, but limited capability, which is, it is a 16-bit, 2-byte instruction. I was going to read only these 2 bytes, guys, in this case, only these ones, okay? Actually, in the previous lecture, we have done these examples on Kale. Please watch the previous lecture as well, okay? You will get a solid idea of what is LDR and what is LDR-H, okay? I think this explanation should be enough.
Tamamdır hocam.
Plus, watch the previous lecture as well, okay? Because it's very clear there, we do operations. Okay, before we continue on Kale, I'm going to be talking about some directives. You remember what directives were, right? Because we have a code. These are the codes. When I say code, I mean assembly codes. Before the assembly codes, there are a bunch of lines coming before the codes because I'm teaching you the instructions. I'm not talking about the code that comes before the instructions, which are called the directives. As I always said, as I previously said, in any language, not in any language, high-level languages like MATLAB doesn't have it, but in Python, in C, in Java, before you start your code, you have some directives, so-called directives before the code. They are different from the language of that code. Actually, you are telling things to the compiler. What is a compiler? But I know that this is not an embedded systems or embedded programming course, but this is a concept maybe you should understand. You write a code, and it is being loaded to the card when you press this button, right? It is being loaded to the card as a machine code. So somebody, actually it is the compiler inside Kale, is converting this assembly language to a machine code. Machine code is binary numbers that the microprocessor understands. Remember the first week, we had a very basic microprocessor architecture, and there was program counter, and the program counter, there was instruction memory connected to it. In the instruction memory, we had some bytes, some binary values. Because of the wiring and the connection of the binary values, those values inside the instruction memory decided what the arithmetic logic unit would do or which register would be chosen. Remember those. Actually, those bytes are the machine codes. So your lines of code here are being converted to instructions, and they are put into the instruction memory. Please. Question? No. Okay, continue. So that instructions being converted to machine code is the code that the machine understands. So this is the lowest code that humans understand, and after that point, when it's compiled, it is the machine code that you have difficulty to understand, but the microprocessor would be easily understand. So guys, so there is this compile operation. And when does this compile operation takes place? I press save, and when I say rebuild or build, it is compiling. Actually, it's converting your code to machine code. Now it's machine code. When I say load, it is being loaded to the instruction memory of your card. That's how it happens in all embedded programming. This is going to happen. So it's the way it works. This is the framework of how you program embedded systems, guys. Okay. So what about these directives? These directives are, you are telling things to the compiler because this is all about the machine code. But you want to say something, for example, hey, compiler, I'll be asking you to compile my code. Here is my code. Okay, I know you can easily compile it. You can convert it to machine code, but also do something for me. Put this code in some part of the instruction memory, specifically somewhere. The compiler will say, okay, I can do that. Those kind of things are compile time operations, because you are telling the compiler to do something while it's compiling your code. So if you want to say something to the compiler, which is about the compiling operation, those are directives. And that's the definition of directives in computer languages. And I'm going to be teaching you two directives today. They are important and you're going to use them. The first one is the EQ directive. Let's get to the definition of it. Which is the EQ? It gives a symbolic name to a numeric constant. Guys, imagine you've got a constant. You've got a constant, whatever it is. It's a value. You're going to sum this value with everybody. And you don't want to write the same value over and over again in your code. You want to name it. Because when you're writing numbers, you can make mistakes. When you write a complex number like this, you can make a mistake. But you don't want to write it. When you say this, the compiler will think that whenever the compiler see this word, seed, it's going to replace it with this guy. Very simple. So let's get to the code. For example, I'm saying that, hey, compiler, whenever I say seed, understand this number. And be careful, this number is a decimal, not an hexadecimal. So guys, let's run the code. And let's see what the compiler does. I'm compiling it. So I have a breakpoint here. I'm just going to jump there. Now, guys, I've defined seed with EQ. Forget M. I'm going to be talking about it in a couple of minutes. So I'm just going to follow it. So I'm going to get the value of seed and load it to R0, right? The value of seed is this. This is a decimal number. The compiler is very clever. It's showing me the hexadecimal value as well. So whenever the compiler sees the word seed, it's going to understand this value. Hexadecimal 0 cross 075B CD 15. And if I say F10, that exact value is being loaded to R0. So it is like something for your, convenience. You're a programmer. You want to write codes in an easy way. You don't want to just write this number all the time because it's difficult to write. You say seed. It is defining constants. And there's a very simple modifier, a directive in C language. Does anybody remember it? Any C guys there?
Hocam define miydi?
Define. There's define and there's also const, which is
Aynen. Evet.
Constant, yes, const, which stands for constant. So if you want to define a constant, use EQ. So if you see a code in Kale like this, definitely somewhere in your code, somebody have defined these guys. So you don't know where, you cannot find it in the code. Right click the seed. I have right click seed. Go to the definition of seed. It couldn't find it. It couldn't find the definition of seed. I don't know why it does, but it's here. Here is the definition of seed, guys. It will take you. I don't know why it doesn't, but it should. Okay, that's how it is. That's a constant. I think we are clear with what constants and EQ are because we're going to use this. And if you need more information about Kale supports, you just can go to that website. Just let me for a second go there. Could not be found. Great, I'm having two Murphy moments. I'm going to just find the link. Don't worry, you can find the link when you Google it. And the next directive is, guys, space. Well, this is about allocating some space in the memory. Why would we do this? Guys, you're designing a microprocessor code, and your instructions will be working on some part of the memory. Usually, the memory should be allocated before you're using it. That's something about compilers, because memory, there are things about memory that we don't talk about in this course. In embedded programming course, we talk about embedded systems course, we talk about them. The memory at start initially is not allocated. You cannot touch it. So your program or your compiler should change necessary bits in somewhere to make those parts of the memory accessible. And this is how you do it. You are telling the compiler, hey, compiler, I've got a code. It's an assembly. Please convert it to machine code and I'm going to load it to the card. And that code will need some place in the memory because I've got some data. I'm going to put it into the memory. Can you allocate some part of the memory for me? You do this by space and these directives. You allocate the area. It means it will be in the data memory. When you say export M, please, whenever I write in this code, recognize M, and it's going to be 4 cells. 4 cells. Each cell is 1 byte. It's going to be 4 bytes. And when you say space, it's going to be zeroed. Every place in that part of the memory will be zeroed in compile time. So when the first line of my code starts, the compiler had already allocated that part in the memory. 4 bytes here because of this 4 bytes. Made them all zeros and has given you the handle for it. Hey, here is your M. What is the value of M? I don't know. I can learn. I'm going to learn, but I don't have to because I'm going to call it M. How do I do it? So guys, as you can see, I've got this. And I have M here. So what am I going to do? I'm going to be running this code. So I'm going to be jumping to the first line of my code. I'm here. So I'm doing F10. The value of M was loaded to R2. Let's look at R2. I see where it is now. This part of the memory, starting with this point, 4 bytes of memory is allocated for me, guys. Okay? Is allocated for me. Wonderful. Wonderful. I'm going to be, so I've got the value of seed here, R0. So store the value of R0 to R2. So I'm going to be writing this value to where R2 points. Okay. So that value of R2 is being written here. As you can see, the most significant byte to the highest address, next one 5B here, CD here, and the least significant byte being written to the lowest address. And it starts with 20 million because M is equal to 20 million. Who decided that M is equal to 20 million? The compiler did. Compiler said, okay, you need 4 bytes of memory. I'll find a place for you. And he found a place for us. We just didn't say where. Okay, just write it there. I don't care. Just find me a suitable place. And looking at the data memory allocation, it decided that place. Why this is important? I mean, in a stupid code like this, it is not important. Everybody, everywhere is available. But imagine you have got a long code with many variables in an end. And somebody should manage where to put where. That's the compiler. You do memory allocation. Anything close to it in C or C++? C, guys, what does it look like in C or C++? I can hear you. Does anybody remember? Yes.
Pointer'larla yapıyorduk hocam. Onda da memory
yes,
memory allocation ama.
We do memory allocation thing using pointers, but what was the command for memory allocation in C?
Hocam hatırlamıyorum valla.
Yeah, exactly. It was something like this. Malloc.
Evet.
Malloc. So guys, actually malloc is also a compile time operation. So when you write a C code, it's being compiled into machine code and compile code. This is not about this course, guys. I'm trying to give you a perspective of how compilers work. Because as a microprocessor guy, you need to understand how compilers work in general. So this is beyond the context of this course, but I'm trying to give you a perspective. Okay, I think you get an idea about this as well. So whenever you see something M or seed, go to the directives and try to understand what it is. Is this an area allocated in the memory? Or is this a constant defined by the guy who wrote this code? Okay. Any questions about EQ and space? No, I think you got it. It's pretty much simple. I mean, when you do coding on your own, get your hands dirty and with hands-on experience, these are pretty much easy stuff, guys. Just you have to try. You have to try. I know that you're doing. Don't worry, guys. Okay, so I'm going to cover an example today. Wonderful. I'll try to do it very frequently, you know. We are going to be working on a random number generator. This random number thing in computers is a bit strange stuff, guys, because randomness is a philosophical subject. We still don't know if the universe is random. Some physicists think that the entire universe is deterministic. So for some people, there is no randomness. And you may argue that as well. Some of you will think that, no, we have free will and I can create random things. I'm going to say something random to you. The other person with a deterministic point of view, philosophical view, would say that, no, everything is deterministic from the start of the universe. You were meant to come here and say that random thing, he or she would say, right? So randomness is a philosophical issue. We won't be able to solve it for people, but we can solve it for microprocessors. And I'm going to tell you that microprocessors are deterministic things. So it is quite impossible for them to create random numbers. However, when you've seen C codes or MATLAB codes, you create random variables. There's a command for that, rand, and it gives you a random variable. How come? I mean, who does that? We are still not sure about the randomness, philosophical definition of randomness in life. How does it do that? Actually, it does not. It is giving you something called the pseudo-random variable. And pseudo in Latin means it is not real, not really random variable. So let's see how it does. This is the code. These are the directives of the code. I'm going to show it in Kale, don't worry. So what I do is I define a constant. It's called seed. I'm going to do it again in Kale. And I specify a place in the memory. Okay. And I've got a code. These were the directives. And I've got an example code. This is the code. This is a function. In a main code, I'm calling this function by BL. And the name of the subroutine, sorry, this is the main code, not the function. You can see this is the main code, and this is the function. We are going to get there. So what do we do in main? I put a seed value, constant seed value I've defined in the previous slide, put it somewhere in the memory called M, and I push M, the value of R0, that seed value, to the stack, and I call the random function. And each time I call the random function, I push the value inside R0, and when I finish with the random function, I pop the value inside R0. So most probably this random function accepts a value in R0, and the output is written to the R0 as well. Okay, so what does this random do? Guys, let's see the random function. So it's okay for now. Let's get to Kale. So guys, this is a random function. Where is it? It's a long code. Don't worry, but we are not going to be using most part of the code. We are going to use this part. This subroutine creates a random number and writes it to stack. It also gets the previous random number from the stack. Why to and from the stack? Because it was your assignment. This is R. So we define the parameter passing. So this function was designed to be a parameter passing by stack function because we want it to be so. So what does it do? This random function reads a value from the stack. The topmost value at stack is read. Most probably when this function was called, main pushed a value into the stack. Did it really do that? Yes. Before calling this function, we pushed a value. Which value and why? We are going to get there. What I do is, I have a constant value here, another constant, a stupid constant value. I load it to R1. I multiply R1 with the value I got from the stack, because it is in R0 now. And I write it to R0. And I write the new value to R1 and I sum it with R0. I'm doing a very stupid operation, guys. Can you see that? What the operation I'm doing is, I'll try to put it in simple terms for you. Imagine I had a value in R0. I'm getting R0 times R1, which is a constant, okay? And writing it to R0. So this value is being written to R0 now. And this value is actually 16. Okay, then I'm summing this value with, that's the operation, can you see that? And I'm writing it to R0. Okay? Then what I'm doing is, it's a long number, it's a stupid number. It's a stupid number, right? I mask all bits except 0, 1, 2. How do I do that? I'm ending this R0 with 7. What is 7, guys, in binary? Because I'm going to be doing a logical operation. And it is bitwise AND operation. All 32 bits will be bitwise ANDed. So 7 in binary is many zeros, sorry, totally many zeros, and 0, 1, 1, 1. So let me just try to put it for you. Like this, right? So this number is a big number. Most probably, I don't know, it is, this number is most probably something like, I don't know, it's ones and zeros, ones and zeros, and ones and zeros, and ones, okay? So what am I doing is, I am ending this number with this number, right? So whatever these values are, they are not important. The last two values is important because when you do an AND operation with 1, you get the exact same value. The others will be 0. If these values were not 1, 1, 1, 1, 0, 1, then I would get the same value. So if this is 1, 1, 1, it will be the same. So actually, I am masking all bits except the first 3 bits. So the number becomes something between 0 and 7. Did everybody understand what I did in this line? So whatever the number is, I'm killing all these bits. So it is something, I don't know what it is. That could be anything. 101, 111, 011. I'm only keeping that value. Good. So this is either 000 or 2111. Something, there are 8 probabilities. And I add 1 to it as well. Now it is 1 to 8. It was 0 to 7, 1 to 8. So the number at R0 is either 1, 2, 3, 4, 5, 6, 7, or 8, 7 or 8. There are 8 probabilities still. And I push that value to R0. I don't know what the number is. It depends on the number at R0, right? Okay, so you get an idea what this code does. It gets a value at R0. It does this stupid operation. Then it masks all the bits. And judging it the last 3 bits, it becomes 1 to 8, something, 8 probabilities. So what do I do in the main? What I do is, let's get to the simple main in my slides. I read the value seed, guys. The first value at R0 was seed. What was seed? It was written in the previous slides. The seed was a random value. Okay. I write it to R0 because this is where seed is kept. As you can see, seed is 4 bytes, and I've allocated 4 bytes in the memory. So I want to keep my seed. If it changes, I want to keep it in the memory. So at the memory location M, I'm pointing it there, and I'm getting the value of seed to R0, and I'm getting the value of R2 to R0. Sorry guys, this should be, sorry guys, this is a mistake. This is str. Okay. Store R0's value to R2 points. At M, I have the seed value. I also have that value in R0 as well. So I push that value to R0. So at R0, as you'll remember, I have this value. Sorry, I'll get there. This value. Then I make a counter. I'm going to create 10 random variables. This counter is going to run 10 times. As you can see, I make R1 10. I start a loop. I do some operations. Decrease R1. If it is not negative, I jump. So it will do this operation 10 times. Okay. So what is the operation? I push R0. We didn't need this code line of code. This is because we push R0 again, so we don't need this. Actually, so this line of code is also unnecessary. You can delete this line of code. Okay. So at R0, I have the seed. What does the code inside my function random does? It does this. Takes the value inside R0. So I pushed it into the stack. It reads the value inside stack to R0. It does this operation and calculates a number and writes it to R0. And I push it to stack, guys. Actually, that's how you create random variables. You create the random variable now because you don't know what it is. You may say that, well, depending on the value of the seed, it is not random. It is deterministic. Yes. But if you update the seed each time you change this number, for example, with the result, you change seed, for example. For example, in the subroutine, imagine we changed the seed with this value before we masked it somewhere here. Then it will be a chain of random numbers. These are called the random number sequences, and that's how you create pseudo-random numbers, guys. So it is like you create a seed, you create a number out of it, then you use it, then you use it. But the problem is, each time you start your code, the sequence will be the same, right? Yes, it's going to be. So there is no way you can start your program and it will give you a random number. Why is that? Because whenever your microprocessor starts, you start it, reset it, its universe is starting from T0. There's nothing new. Each time we start it, it is opening its eyes to reality for the first time. That's why it is doing everything the same. So in a way, it's difficult to create random numbers. We create pseudo-random numbers. So that's a strange subject. Any questions about what I tried to do in this code?
Hocam benim var aslında. C'de, C++ ya da diğer işte programlama dillerinde genelde random sayı yaratırken sistem time'ına seed etiyorduk da ona benzer bir şey yapabiliyor muyuz burada?
Very good question. What your friend is asking is, whenever we do something about random numbers, we take the seed from the system time. And that's the way to do it in C or C++. But remember something. You're running a C code in an already running computer. The computer was already running. And at some point, that code starts. That's a definition of randomness. However, in your microprocessor, you are starting the microprocessor each time again. It's starting from like the Big Bang each time. So if your microprocessor was already working and you were counting a time and you did not know when the code will arrive, that would mean something. But there is nothing external at this point, right? Because, for example, your code is, your C code, you are seeding it from the clock in your microprocessor. There's an operating system. You start a program. That program, when it started, it created a seed from the time. But you as a person started that program. You are an external thing to the computer. But in our microprocessor, we don't have this. But if you have a structure like that, yeah, that could be. That could be. So you could create a counter, and whenever somebody pushes a button in the microprocessor, you could create a seed like that. That would be more random. But imagine we take no output from outside. In that case, it's impossible. Can you make the difference? No?
Evet hocam, anladım. Teşekkür ederim.
So if there's an external interference, something or somebody, well, yeah, that could be more random. But there are cases that it is not. I mean, your washing machine cannot create random numbers. It has a microprocessor as well. But if it has a timer inside, and if it is counting the time when you're pushing it, that's an external thing. Maybe your washing machine can also create it, thinking that you are the guy who is using the washing machine. So guys, I think that's a concept. I mean, that's a concept that you should learn about microprocessors and computers. Any other questions? No? Okay. The previous week you asked for a homework, not an official homework that I'm going to grade, but for a study homework exercise, which we were going to be covering in the office hour. And I'm sorry, I wasn't able to just send it to you, but I decided to give you that homework today. Okay. First, this random number generator is not finished, guys, because if you're going to be calling random numbers on and on again, you have to update the seed as well. And in this code, the seed is kept in memory location M. So the random number, when it's called, should update the seed. So somewhere here, you should write some codes to update the seed. So write this code, guys. Create this code. Create M seed, just like you see in this video. And write the random number generator. Update the seed inside. And create a sequence of random numbers. Do this for me. Or if you can't, we are going to do this on the office hour. So that's your homework for 2 days. Okay? I think that's a good one. And I'm going to be giving similar homeworks each week. Don't worry. If even one of you, if you could do it, you'll be able to present it. Okay? Good one. Did everybody get the question?
Anladım hocam.
This is not an official homework, guys. This is a practice that you asked for. Okay. Okay, any questions? No questions. No questions. Okay, I think the slides are okay. We are done. Okay then. I think